Okay, so we've talked about things that are alternating. We've talked about harmonic and p-series and geometric, and we talked about others that are kind of harmonic, kind of geometric, kind of whatever. Let's talk about a different type altogether. And this is something where you tend to have either a lot of things raised to a power, or you have things that are, so let's see here, I got there's 4 raised to n over things that are like factorials. I'm not sure why I had there. So n factorial. So things that have crazy variable powers or things that have factorials in them. A great test to use with that is the ratio test. Now, the nice thing about the ratio test is all you have to do is take the next term and divide it by the previous term. So in this case, a sub n plus 1 divided by a sub n, and take the limit. Now, you're going to figure out very, very quickly why this is a nice test. Well, what is the next term after 4 to the n? Well, it's 4 to the n plus 1. And if I were to divide that by 4 to the n, what is super nice that happens here? Well, how many more 4s are in the top than in the bottom? Well, I get rid of n of them out of the top and n of them out of the bottom, leaving me just 4. Well, that's super nice. Now let's talk factorials. N plus 1 factorial over n factorial means I have n minus 1, n minus 2, keep going. Over here I have n plus 1, so the next one is just n, and then n minus 1. You're like, wait a minute, this and this cancel out. This and this cancel out. In fact, the only thing that doesn't cancel out is n plus 1. So you take something that is otherwise infinite and really wild and make it super simple. The conditions are that if you take the ratio and you take the limit, and if that ratio, this is rho, by the way, not p, rho is from 0 to 1, then it converges absolutely, just like geometric series. If it is greater than 1 or infinity, which of course that's like, duh, that's why would you even say that? Because infinity is clearly greater than 1. It's going to diverge, just like geometric. Now, the only difference is in geometric, if it equals 1, it diverges. Here, it's not enough information. It's inconclusive, so we can't say that. All right, so if you take a look down here for an example, they literally take this example, you add 1, add 1, add 1, then you got to do some simplify by flippy floppy, and you get down to this. Now, what happens when I take the limit? As n approaches infinity, I get 0. So wait a minute. If it's between 1 and 0, it's definitely going to converge. So this totally converges. If this were here a 10, then that means it's greater than 1. So it's going to diverge. And what if it actually equals just 1? You'd say, crapola, the ratio test didn't work because it's a 1, it's inconclusive. All right, so that's ratio test. Now, there's a couple more examples here clearly. The last one is the root test. And the reason the root test comes here with the ratio test is because remember a minute ago, we said, hey, what if I have 4 raised to the n? All right, well, that's cool, except it's like infinite. But what if I now also have n plus 1 to the n? Well, now I have like both things raised to the n. Well, basic math tells me that I can do the following. 4 over n plus 1, and everything's raised to the n. Well, let's think about this just a second. If I have a graph, and I have this graph right here, and let's assume it converges. What would happen if I take the square root of this function? Well, it's going to get smaller, correct? So if I take the square root of the function, it's just going to get smaller. So this is the square root of whatever f of x or whatever it is. It's going to get smaller. But we already determined that if I got to converge here and I have something below it, then what guaranteed is going to happen? Well, it's going to converge. Now, likewise, what happens if I have a function like this and it diverges. Well, okay, what happens if I take the square root of infinity? I still have infinity, so whether I take the root of infinity or not, it's still going to diverge. That's basically what the root test says. It says if you have something that you could do this to, where you can put the root outside, it doesn't matter if I take the nth root and cancel this and this out, making the problem far more simple. If this by itself, the thing that was inside is going to converge, it's still going to converge even if it's raised to the nth. If it's still going to diverge, it's still going to diverge even if it's raised to the nth. So in essence, what we're allowed to do is, if the type of problem allows us to get rid of the powers by using the root nth power, then just treat the inside separately and deal with only the inside. That is no more complicated than the root theorem is.